Hello viewers, welcome back to the series of natural language processing. In this video, I am going to talk about the most powerful recurrent neural networks. Simply to say, these recurrent neural networks are useful for processing sequence data. First, let us understand what is the meaning of the sequence data. In reality, the sequence of data is all around us. For example, audio is a sequence of sound waves and text is a sequence of either characters or the words, and video is a sequence of images. Thus, many things around us are in sequence. So, what is the meaning of sequence data is it's a kind of data where the order matters, meaning that the elements are in related to each other in the sequence data. Now the question is how to process this sequential data. The existing artificial neural networks and the convolution neural network models are taking fixed size of input and produces a fixed size of output. But for the sequence data, where the where the number of words in a sentence are different, meaning that one sentence can have a 2-word length and another sentence can have a 5-word length and another as of 10-word length. So sequential data with the sentence is of variable length. In order to process such a data, recurrent neural networks are useful. Let's see an example of we are thinking of to train a neural network to predict the next word in a sentence. Example, this morning I took my cat for a walk. This is the sentence. Given these words, your model need to predict the next word in the sequence that is called walk. In order to build the neural networks which process such a data, that learn this sequence representation of the data, the existing artificial neural networks are not sufficient and not capable of, because they cannot process the data in the sequence order, and particularly to process such a task, a kind of remembrance to the network is important that is not possible with the existing artificial neural networks and the convolution neural networks. So what we need of is just step back and reflect how we humans read a language. So when we read a sentence, we usually scan the sentence from the beginning, one word at a time. So once a word is read, for the next time, based on what has been read so far, is called some sort of mental state. We will figure out what is the word meaning, and then we'll update the mental state until based on whatever the words learned up to that point. And finally, we will move on to the next word. This is a repetitive process that we can do. The final mental state will give the entire representation of this word. This is how a human can read a language. Correct? So this is called incremental way of learning. Now, if you implement this incremental way of learning in terms of operations, it starts with the initial state and update the state by reading the first word in the sequence and update the state by reading the next word in the sequence. So this state updation is happening at a very time step, the meaning that the time step is processing one word at a time in the sequence order. The final state which we are updating after reading and processing the last word in the sentence is the entire representation of the final representation of the entire sentence. This is what called same as the RNA. This is the abstraction for the recurrent neural networks. If you define this RN as a function which processes a list of words starting with an initial state by considering one word at a time, nothing but one time step, it is updating the state at every time step by the current word it is processing. It is updating the previous state by reading the current word it is processing, and finally the final state it is going to return is nothing but the representation of the entire sentence. Thus, recurrent neural networks are particularly suitable when there is a sequence of inputs rather than single input. Looking at this picture, we can understand better what is the meaning of recurrent neural network exactly. In contrast, it seems to be like the standard neural network architecture, but there is a difference that is called recurrent loops in the recurrent neural networks. These we cannot see in the artificial neural networks. So, thus these are similar to the standard neural network, except the memory state which is added to the neurons itself. In this diagram, if you look at it here, at some time step t, this network will take the input vector xt and process the vector and produces the output vector y hat t. Along with the output vector, it is computing another thing that is called the internal state ht and passes this information to the next time step by meaning of the loop, self-connected, so that all the nodes in the hidden layer are connected to each other in the recurrent neural networks. We call these networks with the loops in them are the recurrent because these networks passes information internally from one time step to another time step. So that RNN maintains the internal state ht at each time step by applying the function f that is parameterized by w in terms of both the current input at the time step t and the old state ht minus 1, so that the current cell state will be updated. Thus, recurrent neural networks includes both the hidden state update and the formal output vector. Let's see how these computations actually occur. Given an input vector xt, this recurrent neural network applies a function to the update. A function to update the hidden state ht, which is a non-linear function applied to the added sum of this hidden state information and the current input at the time step t. There are two weight vectors you can observe here. These two are the multiplications of the two weight vectors. Here it is the WHH associated with the hidden state. Here it is the WXH associated with the input. Thus, added with the aggregation of these two together, applying the nonlinear function, it will update the hidden state information. And finally, the output is the modified, transformed version of the internal state. This y hat is the transformed version of the internal state ht, and along with the multiplication of the weight matrix associated with this hidden state to the output vector, that is why. This is how a recurrent neural network updates the hidden state and produces the output. Another way of representing these recurrent neural networks is by actually unrolling this loop over time. So, if you think like that, this recurrent neural network is a multiple copies of the same network where each passes a message to its descendant. The message passes is based on the HT, internal state HT. So, when you chain these models together, you can understand how this recurrent neural network is well situated to process the sequence data. Here, WXH are the weight matrices or the weighted transforms from input state to the hidden state. WHH are the weighted transforms from the hidden state to current hidden state. And WHY are the weighted transforms from the hidden state to the output states. An important thing you need to remember is the same weight matrices have been used at each time step. Now, from these outputs already we calculated. From these outputs, y0 to yt, the corresponding losses will be calculated. L0 to lt. Sorry, this is not L3, it is LT at the last time t. Once all these loss value, which completes our forward process, once these all loss values at every time step have been calculated, the final loss can be obtained by summing all these loss together at different time steps. Since this loss involves this individual contributions over time, this means that in training the network, we will have somehow involves this time component. Next, in recurrent neural networks, errors are back propagated at each individual time step. And they are finally across all the time steps, all the way from the where we are currently to the beginning of the sequence. This is the reason why it is called back propagation through time. Computing these gradients with respect to this H naught involves many factors of this WHS plus repeated gradient computations. If many of these values involved in repeated multiplication, such as the weight matrices and the gradients themselves, are larger, the meaning that greater than 1, we can run into the problem of exploding gradients. We need to optimize them, and one way to mitigate this problem is performing gradient clipping that scales the large gradients to the small gradients. This is one way. Conversely, if you see, we can have certain instances where the weight matrices are very small. With the repeated weight matrix multiplications, we can lead to a funnel called vanishing gradients, where the gradients become close to 0 and you cannot train the network stably. This can be avoided by different ways. One such a way is here are the few methods. One is the changing the activation function. Second is the looking into the choosing the proper weight initialization and setting the network architecture, more enhanced architectures. So first let us discuss, is this vanishing gradients is really a problem? For example, let us consider you keep multiplying a number repeatedly by some number in between 0 and 1. As it is repeating, the number is going to be shrinking and eventually it is going to vanish. When this happens to the gradients, what this means that is, it is harder to propagate the errors further back to the past, because the gradients are becoming smaller and smaller, which means that will actually end up biasing our network to capture more short-term dependencies, which may not always be a problem. Sometimes we only need to consider very recent information to perform our task. Let us consider our example, a language model where we are trying to predict the next word. So in this phrase, the clouds are in the dash. If we are trying to predict the last word, it's relatively obvious what the next word is going to be, and there is not much gap between the key relevant information like the word cloud and the place where we need the prediction. So in this case, the recurrent neural networks usually relatively short-term dependencies to generate this prediction. However, there are certain cases where much context is necessary, like this example. I grew up in France but now live in Boston and I speak fluent dash. Here the most recent information suggests that the next word is most likely the name of the language, but we need the context of France, which is way earlier in the sentence, to be able to fill in the gaps that are missing and to identify which language is correct. And so this gap between what is semantically important grows the standard neural network, recurrent neural networks becomes increasingly unable to sort of connect the dots and the links of these relevant pieces of information together, and that's because of this issue of vanishing gradient problem. So as we've seen in the previous slide, one such a trick is to use the suitable activation function. Both the sigmoid and the tan h activations have derivatives that are less than 1, except the case tan h equals 0 when x equal to 0. In contrast, if we use the ReLU activation, the derivative is 1 when x greater than or equal to 0, and this helps to prevent values of our derivatives from shrinking the gradients. Another trick is to be smart in how we initialize the weight parameters of the network. Initializing the weight parameters to the identity matrix helps in preventing them from shrinking to 0 too rapidly during the backpropagation. But the final and the most robust solution is to use a slightly more complex recurrent neural that can more effectively track the long-term dependencies in the data by controlling what information is passed through and what information is used to update its internal state. This is the concept of gated cells. Many types of gated cells and architectures are there, like LSTM and ZRU, etc. About this LSTM and GRU will be explored in the next video.